So the catalyst for this idea, I think like all good ideas, was having a beer on a hot summer's day. I was noticing the water condensing on my beer glass. It started me thinking about the potential of heat transfer in terms of capturing water. Water scarcity is now the problem of the 21st century, with population growth expanding, particularly in areas that don't have large sources of natural water. This drew to our attention the areas in orange and red that are experiencing very high population growth and ever-increasing water scarcity, especially urban areas, say India, where there is an abundance of water in rivers, but the water has been used in industrial processes and it's not a clean source of water. The needle nature of Vena came directly from that biomimicry. In Chucanga, Chile, one of the driest places in the world, actually has no natural source of water except the condensation on cacti needles. The surface area of the cacti itself is slightly cooler than the ambient air temperature, so water condenses around these cacti. The question is, how do we bring this water to where it's needed?
Because Vena is small scale, the modular design allows potable water to be delivered directly to localized areas of need, thus eliminating the need for conveyance infrastructure. Furthermore, Vena is openly scalable, allowing the number and placement of Vena units to address the size, location, and need of the community. Delivering clean drinking water to the populations of the world living in arid and/or heavily polluted areas, Vena is a radical solution for people living in climates lacking consistent rainfall or clean ground source water.
In desert environments, the daytime warm temperatures are 30 to 40 degrees Fahrenheit warmer than the below ground temperatures, which are in equilibrium with the night temperatures. This creates potential just like that beer glass. If you are able to span the below ground temperatures to the above ground temperatures, you can trigger the dew point and you can harvest water from the atmosphere.
With its biomimetic design, Vena is a low-cost, low-energy solution for the developing world's critical need for drinking water. It extracts water from air by transferring cool, below-ground temperatures to an elevated network of copper alloy filaments, around which latent airborne water condenses and is collected.
The next kind of level of defense against heat gain are dynamically formed ceramic discs, which have a high white gloss to them, so they reflect the sun's heat. These are stackable, just a modular system. The beauty of the exterior shell is it not only protects the interior core of Vena from heating up by the sun's heat, but it also acts as a wind scoop. So the open apertures bring the hot air into the core of Vena, and the air then circulates around the cooled copper filaments. The fantastic thing about Vena is it functions the best in places that need it the most. In areas of highest water scarcity, we have the highest levels of heat differential between above ground, below ground temperatures. You're going to harvest the maximum amount of water in those locations. The green competition seed money would allow us to pursue prototyping funds. And the first prototype we would build would go to our non-government organizational partner in Kenya, Farming Systems Kenya, to test it directly in rural and urban environments in Kenya. It's a situation we all face. So once we thought of this idea, once we started developing it, we got very excited at what a large-scale impact we could provide in relieving the world of a very heavy footprint of needing to bring water through ground resources, which is very limited, and aquifers, which is needed for the ecology of the planet, not just for agriculture, not just for drinking water. So if we can find other sources of drinking water, we can really promote biodiversity.